Okay, this is looking quite a mess, but I'm going to try to explain what's going on here. Some of you may be familiar with our the TSN digital 3-axis magnetometer, and this is the most recent plot from this station, which is on the other side of my house. What I'm constructing is had a lot of help from a company called Fat Quarter Software, and I bought one of their kits, which uses Speak Industries FGM-3 Fluxgate magnetometer sensors. These sensors are extremely accurate and precise. Many orders more precise than the Honeywell digital sensors that are in our lower resolution magnetometers. So you get this as a kit, and this small circuit board right here does several things. It's got power regulation. There is an ASIC, which is a application-specific integrated circuit developed by Speak, specifically for the sensor. So on this board, you got power regulation. You've got a SCL006-B chip, which accepts the output from the Fluxgate magnetometer sensor, and then it sends that to an A to D converter, which gives you a fluctuation range between 0 and 2.56 volt. So what I've got here is there's a bunch of other junk on my breadboard that's not related to this. I'm just basically using the breadboard to give me some power rails, ground and 5 volt. So let's start with the sensor. In the end, the sensor will be buried outside, away from any interference, and insulated for temperature variations. Right now it's inside a cooler at room temperature, and even though I've got quite a bit of computer equipment, I'm seeing very little fluctuations. It's a 3-terminal device. If I could open the cooler, I would. But it looks like it's about the size of, say, take a Philly cigar. Take a regular size cigar, cut it in half. That's about the size and shape of the sensor. 4 terminals on the end. One of them is a feedback terminal, which is not used. So all you need to supply is this wire going to it, this gray wire, is some heavily shielded 3-strand. So I've got ground, a 12 volt line, and it's got one output signal. The output signal is a 5 volt square wave, kind of like a pulse width modulation wave that's between 40 and 120 kilohertz, and that frequency changes directly proportional to the measured field, and it's set up for a range of minus 80 microtesla to positive 80 microtesla, which more than covers the range of Earth's magnetic field. You align the sensor on an east-west axis, so you're measuring a vertical component. So in the end, this will have the sensor will have a little breakout board, and I'm going to use Cat5 cable. So it'll have a RJ45 female Cat5 connection on one end with power regulation. Like I said, I'm sending 12 volt from the Arduino supply, which I'll get to in a minute. And then that gets regulated with a 7805 on that end. So that regulates 5 volt to the sensor, and it sends back a 40 kilohertz to 120 kilohertz square wave that is directly proportional to the field. And I've already written some Arduino software to capture the data, the variations, and calculate the frequency and the field. On the computer, I've got a digital oscilloscope set up, and the output from the magnetometer is on channel 2. That would be the green square wave form that you're seeing. And next to that, I have my Arduino output, which is outputting data once a minute. So it's every 60 seconds it's going to spit out the analog value, which is variation in the field, and the frequency. And I've also added a little algorithm to calculate the field from the frequency, maybe within 1% accuracy. And I'll show you what I'm weighing that against here in a minute. I do have a calibration coil provided to me by Eric Kern at Fat Quarter Software, but I have not used that yet. So I've got this set up to measure amplitude, period, and frequency. And since it's directly proportional, as the field goes up and down, so will the frequency will vary between 40 and 120 kilohertz. So if I was to rotate the sensor all the way around 180 degrees or do a full 360 turn, I should see a variation in frequency somewhere between 40 and 120K. So right now it's outputting, let's see, it's fluctuating between 50 and 55 kilohertz. But the sampling rate on the scope, I'm going to rely more on my Arduino output. So on the oscilloscope probe, I've got one end connected to ground, and I've got the probe connected directly to the sensor's frequency output. That frequency output is also going to a digital pin on the Arduino, and I'm using a frequency counter library to basically measure the pulses on the rising edge. And so with that, I can compare the accuracy of the oscilloscope. Give me 1 second. I'm not the best cameraman in the world, I'm sorry. So anyway, yeah, the frequency coming out of the Fluxgate is also going to digital pin 5, and out of the kit board, the analog output is going to analog 0, and then I'm monitoring voltage. The VCC supply from the Arduino, I'm just going from 5 volt, taking the 5 volt rail and going right into analog 3 to check the regulation abilities of the Arduino. The reason for that, if I see any fluctuation in my 5 volt rail, then I will add additional regulation. I may use a 7809 to first step the 12 volt supply to 9 volt, and then regulate, use a double regulation technique, and then use the 7805 to regulate the 9 volt voltage to make sure that we have a steady 5 volt that does not fluctuate. So here on the Arduino side, this has been running for about 12 hours, and each minute it upgrades, it updates the analog value, the calculated field, and the frequency. Now, according to the Arduino, which I'm going to give it more credit than the $89 digital oscilloscope that I'm using. Like I said, the digital oscilloscope is jumping around between 50 and 55 kilohertz. The Arduino is giving me a steady, it does change over time throughout the day as the field changes, but it's giving me a steady frequency of 52.82 kilohertz. So I'm going to go with that. When this board is reset, this kit board, I've got a little reset button rigged up. Later that'll be controlled by the Arduino. It sets the analog value to a mid-range. It's a 10-bit analog to digital converter on the Arduino, so it's got a range from 0 to 1023. So if the max output of the kit is 2.56 volt on the high end and 0 volt on the low end for any field variations, then on the Arduino, if the kit board is putting out 0 volt, I'll do 0 on my analog pin. If it's putting out its maximum of 2.56 volt, I'll get a value of 512. When you hit reset, it'll zero itself out to halfway, half scale. So if I were to hit the reset button right now, it would take an ambient field reading, and this little board would put out an analog value that is half scale, which would read about 256 on the Arduino. That would be about 1.26 volt, something like that. 1.23 volt. No. Anyway, so when I reset this last night, my analog value was right around 260, and throughout the day I've seen it drop slowly and then rise. So when I go to plot this, it's going to be much like the digital magnetometer, but I'll be measuring much more precise, on the orders of a few nanoteslas and change, without having to use averaging and oversampling. I'll probably be able to take one reading, and that should be accurate enough, or maybe average 3 readings at the very most. But to compare the little algorithm that I wrote to determine field, I'm going to use absolute values. It's giving me a negative value, which means that I could have the sensor 180 degrees off, which could be giving me a different polarity. It's measuring minus 54,380 nanoteslas, which is 54.3 microteslas. And if we look at the digital magnetometer, it's measuring on the BT. Right now it's at 50 microteslas, so that's very close. That's only 4 microteslas difference, and that's probably accurate because these two sensors are about 50 feet apart. That value is being taken in a totally different room, actually with less noise, so that makes sense. I'm measuring 50 microteslas on the digital and on the Fluxgate, and this other room I'm measuring 54 microteslas. So the next step will be to, I've got some more chips on order, and I've also got a more sensitive Fluxgate magnetometer that they don't manufacture, sadly, anymore. It's the same package, it's the same sensor with 2.5 times greater sensitivity, but it'll work with the same kit. So when I get those chips, I'll be breadboarding, emitting the kits and doing everything digital to the Arduino, and I'll be trying out the more sensitive sensor. But I'm just pleased to finally have some readings coming back from this Fluxgate magnetometer, and in the end, the interface software will be very much like the application here. The only difference being there won't be a compass because it's a one-axis instrument. So you won't have 4 plots, you'll have 1 plot, which is all that is necessary to visualize magnetic storms and solar activity, which is our goal. So as development continues, I'll post more updates, but that's where I'm at right now with the Fluxgate magnetometer. Thanks.